All right, welcome to another live stream of 6502 assembly. We're gonna write a method of sorts that computes the nth Fibonacci number. Plus it's going to be memoized, so that's gonna be nice. But let's start with what the hell we're talking about, explaining the point. All right, the Fibonacci sequence is defined by the recurrence relation. I'll assume we have some math capability here, so I'm gonna write the formula, which is just you add the last two numbers to get the next one. And then new line. The first Fibonacci number is 0 and the second Fibonacci number is 1. Okay. So in assembly, the way to think of methods, well, you don't have to, but let's say we're going to define, I guess a method will always has the first argument at the top of the stack. So the argument n of our function will be located at the top of the stack. Now you're like, stack? Where's the stack? So assembly, or sorry, 6502 has a stack. Meaning just memory locations, and it offers a few functions. It offers these two stack instructions, PHA and PLA, so to push and pull the accumulator, push the accumulator to the stack and then pull from the stack to the accumulator, and it uses a stack pointer to know what the top of the stack is. And importantly, it also offers this thing, not this one, JSR RTS. So jump to subroutine and return from subroutine. So it allows you to have returning from a method and stuff like that. So if you can see, JSR, you go to the to whatever the subroutine we will have, so Fibonacci, and then this is basically like calling a function returning, and then you can use RTS to return. So actually what happens if you look, stack moves, and indeed by not one but by two locations, because it's a byte. Wait, a single memory location stores a byte, so 2 bytes, I guess, for addressing, and that's where the address is. I'm assuming, but let's check. So let's observe the stack, which was again at which location? 01FF. Okay, so if I go to 0100 to 01FF, I can monitor this. Not here. 0100 and 01FF, and I can monitor this location, reset, and then that's here, right? As you can see, 0206, that's where we were at. And the explanation for why that's the location is because the PC, if you look at look at the program counter. So you're in the first, and at the same time, probably want to go to this monitor? I don't like this. All right, let's just do this to keep it simpler. I don't know why. Oh, length. Length is what? 8. Oops. No, that's a byte, so we need F16. Okay. Okay, no, it doesn't have the full one. That's not 56. That's 15. Ah. Alright. So now we have, what is this? 4, 8, 12, 16. Correct. Alright, so that's F0 and that's FF. Now if we look at, yeah, let's start at the beginning. Okay, so this is your 600. So that's where that is. Then you will see, what is this jump to do? Oh, you can jump. Anyway, so then of course, by the way, every instruction, as you can see, is 2 bytes. Wait. No, it doesn't have to be 2 bytes. Again, JSR is 2 bytes. Alright, no. Let's just get a few things straight. Okay, I'm losing it. So the idea is the following. You execute an instruction. Of course, the PC will hop to the next instruction. If you go linearly, the problem is this is a jump. So what this needs to do is it needs to save the address of the next instruction to execute once exiting the subroutine. So that's what you will see, because this is 1 byte and this is also 1 byte. I think labels are 1 byte. Yeah, in this case it seems so, at least. You will have 0602 as the next address, and 0602 we expect to see here. So if you go step 0602, again, little endian, therefore you see it this way. So now you're wherever that points, so to 09. Therefore, once you execute the first command, yeah, something changes, and then boom, you will see the PC will be 0602, and then, okay, now I can't explain it. Once you return, why is it 0603? Oh, pops the, wait. The processor knows where to return because it's the address -1. Oh, okay, that's just convention. So it does address -1, and then that adds 1. Okay, so this instruction indeed was 3 bytes. So probably addresses are 2 bytes, and this is 1 byte opcode. Okay, explains everything. All right, very good. So that's kind of how subroutines work. So now I would really like to have this sort of assembler, not here, definitely easy6524. I would like to just download this and run it as a so not the whole tutorial, but I'd like to run the assembler layouts. That's the simulator widget. Is there a nice way to use this? Okay. Can you call? 1 sec. Okay. Yeah, so I'm trying to get this to run locally and not have to use all that stuff. Okay, let's not even forget the one for I just want to clone the repo somewhere. Okay. Just here. Just sort of easy. What happens if I server web server from here? Okay, just copy directly. Index markdown doesn't do anything. Yeah, there's no website here, naturally. Okay. What is this index markdown? Ah, that's neat. I don't want that. Okay, layouts. What if I copy this basic layout and call it index.html and try to see if that's servable? Okay, it is. Okay, and now I need to find out. I need to, oh, there's a branch here. What is this? Okay. Content. I would really like to go to layouts and try to find one of these. Definitely one of these things. No. Widget. This is sort of what I wanted. This is exactly what I wanted. So if I will copy. Okay. Okay, let's try this again. Hey, does this work? Wait. Oh, it does. Perfect. This is what I wanted. Okay, I just want this site. Egg stump. Blah 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 blah. Okay, perfect. Perfecto. Okay, so now we have our assembler. Okay, and this is our reference. So what we're gonna do is we're gonna call something Fibonacci or Fib. Okay. And the idea is this thing is supposed to, but this doesn't return any value. So okay, let me try to understand something. Once you pop, what happens? All right, let's go step by step. You have that. Okay, so nothing is saved on the stack really except that return address at the top. By the way, from what I know, let me try this. Yeah, the stack goes in this direction. So the problem I'm having here is that I also want okay, after returning I want to save the value at the top of the stack. Or should I do it in the accumulator? Yeah, this is a problem. I think top of the stack makes sense. Alright, so my commitment will as well implement the computation. Okay, that's the promise. That's the promise. Okay. I don't know if that's sound idea, but I think that's how things do it. Like when learning about x86, that's how I remember it was. So maybe I'm wrong, but anyway, that's my approach. Okay, so the idea is Let's do naive Fibonacci. Naive Fibonacci. Okay. What can we do for naive Fibonacci? We can just do an iterative algorithm. So store 0 and 1 somewhere. I would like to store them in some registers, but it's complicated, so I'll store them. I'll store them in memory. Okay, so I will say use memory location. I guess stack again. Again, use the stack. Okay. So we'll write this like this. Int f0 or f1. Okay, I'm gonna assume this is some C code. Okay. All right. And f2 is 1. And then we want the nth Fibonacci. So for int I, let's say equal to 3, I is equal to n, because we have the first and second. We will say fn is equal to 0, we'll start with, and then fn we will say is I'll say, okay, now I want to say previous, right? FPP, previous, FP and F next. Okay, let's do that. So Fn is equal to Fp plus FP, and then Fp becomes FPP. Oh, okay. Do I need a temp variable? Seems like I do. Or do I? And then I want to do FPP is equal to the previous Sn, so sort of like Fn. No, let's do this. FP is Fn minus I'm confusing myself. I'm confusing myself. I'm trying to be clever without temp variables because I don't like temp variables, okay? So you don't even need 3 variables, that's the thing. I think so, right? Right. Okay, let's try it. Let's try it with 3 and 5. Okay. So then this becomes 8, and this becomes 8 minus itself, which was 3, is 5. Yeah. Okay, that works. Essentially, you want it to be the previous value has been sort of already increased, so you need to sort of decrease it. Okay, that's it really. And then you return FPP. That's the function. That's our function. Okay. Let's go left side. Okay, okay. Okay, so right, and then actually you don't even need memorization, so it's not even naive. Naive would be recursive. So this is fast. Okay. Okay, so initially on the stack, what will stack at start? Our stack will have at the start, at the top, return log, and then it'll have n and empty, 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 right? That's our stack. So what we'll do is first step, push 0 and 1 to stack in that order. Okay. So we will go. We want to learn how to push to the stack. So first we have to load the value 0, push. Where the PHA. We have to load the value 1, PHA. Okay, that's done. Then I want to access n. So I would like to load in the accumulator the address at SP minus 2 bytes. Okay. LDA. Okay. Memory. Right, with absolute, so SP. So is it possible to do? Yeah, I need to see. I need to. What are some ways to? Absolute, indirect. Index indirect is what I want, kind of. Is it possible to do something like? Does it even assemble? Oh, it does. Okay. Okay, what happens actually if I monitor the stack here now? What was the stack? 0 and then 120 monitor assemble. Yeah, not that. Ooh, okay, it's not working. the documentation for LDA somewhere here. No, need better documentation. I need the stack pointer, okay? I need the stack pointer. Or okay, what if I do sort of the opposite? Like 0 as X. Okay, so somehow it doesn't recognize SP? Is there okay. Oh. Okay, stack. I guess you'll need to use oops. What the hell happened? This is running fine. Oh, it was still running fine. Okay, and then let's do DSX. Of course. What was the stack again? I keep forgetting. Well, nothing will happen, of course, unless I do something like what was the stack? What was the stack? What was the stack? 0 FF, correct. Okay, debugger. Fib LDA 10, whatever. Okay. And this doesn't return. Returns, was it called? Oh, no. RTS, okay, RTS. So why doesn't this work? Again, let me remember what location it was. The stack 010001 FF. That's 01 FF. Stack pointer FD. Okay, F. I'm looking at the wrong location. Okay, this is cool. Okay, so that works thus far. What's this? TSX? Okay, so I need to also do TSX and then let's say some value 8 and then how to write something in a memory location. STA. I think that works the same. I just remembered. Does that work? This anyway will override it, so no, this doesn't work. Wait a second. Right? Oh, okay. Let's look at this. So X has FF. Probably need to do something like this. Oh, that works. That works. So if I do, and instead of going over the stack, I need to go back. So I need -2 here. So I need something like E, something like that. No, okay, if I go by the way with A, what happens? So with 4, that happens there. With 3, it'll happen here. With 2, here. This is called taking 1. Hey, let's do this. Yeah. So A, B, C, D, E, F. So if you write FF, that's taking 1. -1 byte. Okay, I need -1 byte. So I need it here actually. It's -2 bytes, okay? 2 bytes. So, boom. And then No, because it'll be overwritten. I mean, I'm doing manual stack management, is it? Is it possible to manipulate the stack pointer? No, apparently not. Or rather, yes it is. Transfer X to stack pointer. Yeah, TXS. 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 I wonder if there's a other way. Subroutines, arguments. Wait, so they're saying to put it in line in the programming. Oh, that's clever. So what you do is that's a great idea. So what you do is this. You know that your return address will always be on your stack pointer. So if your next instruction is exactly the value that you're trying to give, let's say 1 byte, for example, then what you can do is rely on the fact that your return address will be pointing to that or that -1, and you can use that to go there and pick the data. And then on the RTS, you will manipulate the stack pointer so that it hops over the data area. This is not easy. Okay. Okay. 1 second. Need to take a little break. I'm back. Okay. I'm back. Okay. So there are some cool ideas out there in the world. Okay, let's see how this is done. Passing parameters. Okay, this is actually the general thing I wanted to know. So you can do web process registers. By variables in RAM. Okay. Let's just put it in the goddamn in one of the stack in one of the registers. Alright, let's just do that. Make life simple. So yeah, we're gonna have the input at x. So we're going to load x, push it, and then that's it. Okay. And then in x we can put like a value 10 or whatever. Okay, so let's do that. And then to access stuff, I'm going to tell you how I do it. Okay, so stack pointer has been moved to FA. Okay, I need to delete one of these, so I'll keep this and I'll delete this. Okay, so I'm gonna, instead of doing all this complicated stuff again, as I said, I'm gonna have LDA BJ here, just LDX 8, for example, whatever. Right. Ooh. Transfer X is TXA, so not really X, okay? TXA. Right, let's okay, whatever. Okay, so we will have 1 0 1 as you see here. Okay. So now that's just the priming of the result. And then in Y, can you even do that? Is there a command? Okay, no. So I'll actually no. At this point, I can still use X again for accessing the stack. And I did find a way. See, this is where you should save stuff. Something like that. Somewhere like here, yeah. Okay, whatever. Okay. So what we want is I'm gonna write a bunch of commands how to access n, access in my program. I called it, what did I call it? FP and FPP, FP and access FPP. Probably some variables would be nice. The way this guy, yeah, does this. Okay, define FP, define. All right, so I'll go. All right, define nlock, define FPP lock, and then define FP lock. Okay. That's just a stack pointer, not a FF, not E, so it's D, C, and right 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. No wait, FF. Was 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, B, C, D, B, C, D. Okay. Right, that's all I need. And then I'll do the following. Okay, I'm going to use I'm going to load the accumulator and lock. I'm going to compare it with okay, I'm gonna store transfer no, see, what am I doing? Just LDX, put 3, okay. And then compare, okay. Compare this with, first of all, I need to find the jump instructions, okay. Okay, so we're going to compare with X and location. What does CPX again do again, please? Right, so compare that with N. Fib done. whatever, some return, that return function that we have already has, okay. Jump not equal fib done. I think they have a JNE. Jump or BNE. BNE. No, sorry. Otherwise, you continue. Otherwise, you continue. And you do this, you do what's this thing called? I do FP. So first of all, you load off PP. You add with carry the value vlog, then you store accumulator in fvlog. Then you do the same. If you load and then you subtract with carry now carry fpp log and then you store in fpp log. Okay, and here you need to set the carry. Okay, set the carry, set carry. I need this table, man. CLD, clear decimal. Set carry SEC. Okay, you need to do that. So that's done. And then you jump to loop, keep doing that, and then okay, if I run it, okay, first of all I need to store the value 5 and then store that in nlog. No, oh, or rather LDA the value 5, right? Because I said that the n is going to. Okay, so things are working. Okay, let's see. Okay, so let's start at the beginning. We have the memory location. Okay, first step we have no. Okay, still doesn't work. Okay, so first step we have value 5 is there. Then we jump to fib with our location. We've got tx transfer. Okay, so we have the value 5 there. Then we have the value 0 there. We have the value 1 there. And now we put in x value 3. Okay, and now you compare x with nlog. That says okay. Let's read what cpx does. Okay, comparisons. So if the register is greater, or if it's less in this case, no, the register is less in this case, so it's 0, carry 0, and ZC, just a sign, okay, whatever. Then it goes to LDA. Accumulator gets the value 1, adds the value 0, nothing happens, and then that's stored. Two, 3, 2, 5. Okay, so this works. Oh, I'm not incrementing my loop. Yeah. Okay. That was rather obvious. So is this the 5th Fibonacci? 3. No, this is the 4th one. Something's wrong. No, that should be 2, I guess. Got it. It actually works. Well, no edge cases yet, but I need to know, okay, if I want the 15th Fibonacci number, that's 79. 9, okay, and then Fibonacci sequence calculator, whatever. What was the number again? Forgot. 15th, okay, and 14th, and 15th. Okay, something is wrong. Or is this not starting with 1? Is this? Well, still doesn't matter actually. That's the wrong number. Times 16 plus 9, that's 121, but that's not correct. Alright, so let's start with the 6th Fibonacci number. And the 10th Fibonacci number is saying that it's 2 times 16 plus 2. Is that even possible? Just give me the Fibonacci sequence. It doesn't look like it. Okay, or the first. Okay. Okay, so 2 times 16, that's 20. I mean, sorry, 34. And oh, it is. So I put okay. So I did get the 10th one de facto. Okay, I think, well, I have a limit, right? With probably 12 is my limit, or 13. When I get the right answer, 90. So 9 times 16, that's 144. And then after that, no, I can go probably one more. It's 249. Oh, is there an overflow there? I guess so. Wait, let's look at this step. You got 9 times 16 plus 5 times 16 plus 9. That's 233. It should be 233. No, 14 times 16 plus 9. So it is correct, but I think after this it just stops working because there's an overflow. I mean, that's smaller than that. Okay. So it does work. Now I just need to comment it, okay? Fibonacci subroutine. Calculates the nth Fibonacci number. N is stored. Is supplied in register X. It is probably best here to comment here. Okay. Okay, what is this? Okay, so that's the function. Pretty neat. Okay. This was nice. Yeah, of course, the limitation is 1 byte, so I can't compute much, but it's cool. I wonder, well, with 2 bytes, we probably could get up to that, which would be nice, but I don't know. I mean, Fibonacci, wait, it grows exponentially, doesn't it? So, no, or does it? Fibonacci closed formula. Yeah, but I don't know the values of these two, but it looks, yeah. Okay, no, so these are just, oh, these are the 2 roots there, yeah. Fibonacci sequence graph. Fibonacci grow exponentially. Yeah. So, not much you can do, but it's a good first program, I would say. And quite a lot of fun. I still would like to do these more reading material. So this is cool because you can do a lot of cool things here. I mean, my idea of stacks was, as I said, you kind of use the stack pointer to add stuff before you return, but that got messy because you had to remember that then you had to update the stack pointer, blah blah. So yeah, need to think more deeply about how to do it, but that the fact that this this approach works is good enough for me right now. Iterative. Okay, so clear carry for subtraction. Oops, no. Set carry. Okay, by the way, I have this program. I need to try something. Does this assemble? Ah, no, not that. That's already location. Boom, boom, we get now the result in the accumulator, correct. Pretty cool. Okay, that's it. See you some other time. Maybe, yeah, my other plan is to do the game of life, or to do 16-bit adding here or something like that, but game of life would be nice. Yeah. Alright.